Hello everyone and welcome to our calculus notes for section 3.5. Today we're going to be talking about limits at infinity. So we take a break from our derivative stuff here and we're really focusing on helping us to graph any type of function. And the limits at infinity are used to describe the end behavior of a function on an infinite interval. So let's take a look at the graph 3x squared over x squared plus 1. So you can see here that it kind of slopes on down, curves, goes to 0, slopes on back up, and then curves. And this function has a horizontal asymptote at y equals 3. And you can see the dotted line right across there. Okay, so the function will get close to that, but will never reach it. And so we can see the limit here as x approaches negative infinity of our function equals 3. And as the limit as x approaches infinity of our function, it's going to equal 3. And that brings us to the definition of a horizontal asymptote. So the definition of horizontal asymptote says the line y equals L, and L is just a number, and so we know this is a horizontal line, is a horizontal asymptote of the graph of f if the limit as x approaches negative infinity of our function equals some constant L, or the limit as x approaches positive infinity of our function equals some L. So in our first example, it says find the limit as x approaches infinity of f of x equals 3x squared over x squared plus 1. So what we're doing here is we're trying to find the horizontal asymptote. Okay, if it even has any. Okay, and this limit at infinity is going to help us find that. If we want to find this limit, it's going to be the limit of the numerator approaching infinity over the limit of the denominator approaching infinity. So if we think about it, if we plug larger and larger numbers in here for x, this is going to increase without bound. So we really get infinity here. As we approach larger and larger numbers, this is also going to increase without bound. So we get infinity over infinity. Well, what we were expecting was y equals 3, and we can see here in our graph that it's supposed to equal 3. So why didn't we come up with that? Well, this is what we call an indeterminate form. So limits in indeterminate forms. Indeterminate forms mean that you have not yet determined an answer. When you see something like this, it means, we didn't quite get the answer yet, but an answer still exists. Some other indeterminate forms you might see are like 0 over 0. Okay, so that means we need some other processes to be able to answer this question. So we see this here. If r is a positive rational number and c is any real number, then we know the limit as x approaches infinity of c over x to the r equals 0. Okay? So if we try example 1 again, we're going to try dividing both numerator and denominator by x squared. Okay, so we're going to divide this part by x squared, and we're going to divide this part by x squared. Now, the reason we're doing that is we're trying to get that constant in the numerator. Okay, so if we divide 3x squared by x squared, we do get a constant of 3 in the numerator. And that's what we were trying to do. Now on the bottom, we're still going to have x squared plus 1 over x squared. And so we're going to have to do a little simplification work on this right here. So we still have our 3 in the numerator. Here we can go x squared over x squared is 1, and then 1 over x squared is still 1 over x squared. So if you look at this part right here, this is 1 over x squared. That looks exactly like this. And so we know its limit is going to equal 0. So I guess let me rewrite this with the limit in front. It's easy to get lazy and not put this, but that's what we're looking for, the limit as x approaches infinity. We would get the limit as x approaches infinity of 3 over the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x squared. So we know we can do that with our limits. We just split all that up, and so our final answer here, well, the limit of a constant is just that constant, so it's 3, so the limit of 1 is just 1, and then here the limit as x goes to infinity of 1 over x squared, it's in this form right here, so that's just going to equal 0, and our final answer is just 3. So again, what that tells me is that the horizontal asymptote is at y equals 3. Alright, so that does work, but it becomes a little more tedious to find our answer. So what we want to do now is look at some different guidelines, and we have a little saying, Bobo Botan eats DC. Okay, so you can also try to memorize this, Bobo Botan eats DC. What we're saying is if the degree of the denominator is greater than the degree of the numerator, then the limit is 0. Okay, and that's our Bobo. Big on bottom equals 0. Okay, big on bottom equals 0. And this is really what we were looking at when we had this right here, c over x to the r. So if this increases without bound and this stays constant, we're going to get a 0 for our limit. Now if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. So this is big on top, n. So big on top equals none, meaning that the limit goes to infinity or negative infinity. So if we were to switch this around, right, and we had something larger on top and our constant on the bottom, this would go to infinity or negative infinity without bound. And the next one, if the degrees of the denominator and the numerator are equal, then the limit is the ratio of the leading coefficients. And that's our eats dc. And eats stands for exponents are the same. And then dc means divide coefficients. Okay, so in that case, we would have the same exponents on top and on the bottom, and then it would just be a fraction of their coefficients. Now note, rational functions always approach the same horizontal asymptote to the left and the right. What that means is we don't have to try a negative infinity and an infinity. We could just try the limit at infinity and it's going to be the same. Okay, so let's try our example 1 again by comparing the degrees of the numerator and the denominator and then deciding what to do. So here we have the limit as x approaches infinity of 3x squared over x squared plus 1. So with this rational function, the polynomial on top and the polynomial on bottom, you look at the highest power, the greatest degree here. And in this case, it's 2 and 2. So here, the exponents are the same. Eats dc. Okay, so exponents are the same. What we need to do is divide those coefficients. So the coefficient of this one is 3, and here it's 1. So we know this is going to equal 3 over 1, or 3. And so again, our horizontal asymptote was y equals 3. And so we've found 3 a couple different ways. We found it graphically. Okay, you can see that this is approaching 3. We did this thing where we try to get the numerator to equal a constant. Okay, and we found that it was 3. Or we can use a little shortcut rule where we saw that the exponents were the same, and so we just had to divide the coefficients. Alright, let's give a couple of these a try now. Let's follow these guidelines right here. They're going to save us a lot of time. So if we want to find each of the limits, first just verify that they are rational functions. The exponent here is 1, and here the exponent is 2. So in this case, it is bigger on bottom. So big on bottom 0. So the limit here has to equal 0. Now let's take a look at what that graph would look like. Okay, so here is 2x plus 5 over 3x plus 1. And you can see as we go to infinity that this guy is going to 0 if we go to infinity or negative infinity. So the graph verifies our answer. For the next one, here we have 2x squared plus 5 over 3x squared plus 1. So again, we have a rational function, and if we look here, the exponents are the same. So exponents are the same. So that's eats dc. So exponents are the same. dc is what we need to do. So divide our coefficients of 2 and 3. And so this limit is 2/3. Let's check our graph now. Okay. And you can see as we go to negative infinity that that's sticking real close to 2/3. If we go to positive infinity, you're going to see the same, still staying very close to 2/3. So what that's telling me is my horizontal asymptote is at y equals 2/3. Where was the horizontal asymptote here? It would be y equals 0. All right, and one more example here. Here we have 2x cubed plus 5 over 3x squared. So compare the exponents. In this case, it's bigger on top. So this is our bottom. Big on top, n, standing for none. So what this means is we're not going to have any horizontal asymptote. And let's just take a look at the graph and see what's happening there. Aha! So you can see the end behavior here as the top. If the top is bigger, it's going to increase at a greater rate than the bottom and is going to eventually eat it up. And you can see here we don't get a horizontal asymptote. Instead, we have an asymptote that runs diagonally right through here. So anytime it's bigger on top, you are going to get this type of asymptote right here. But today, we're really concerned with horizontal asymptotes. So next we're going to look at finding limits at infinity of non-rational functions. So functions that are not rational may approach different horizontal asymptotes to the right and to the left. But we can still use the same procedure as before to find these limits. So here's a couple functions with two different horizontal asymptotes. And so we're going to look at the function 3x minus 2 over the square root of 2x squared plus 1, and we're going to find the two different asymptotes. So you can see right here, this is a non-rational function because of the square root. So we have a radical here. And you can see here, as we approach negative infinity, we're getting closer to a different value than as we approach positive infinity. So to find the different horizontal asymptotes, we're going to look as x approaches infinity, as well as x approaches negative infinity. So when we look at this, we have 3x over the square root of 2x squared. And when you think about x and the square root of x squared, they really have the same power. Okay, so this is really to the first power, and this is the square root of x squared, which is also x to the first. So this is really a form of our eats dc. So when the exponents are the same, we divide coefficients. So the coefficient of the numerator is going to be 3, and the coefficient of the denominator was going to be the square root of 2. So you just have to remember to keep that square root in there. Now, you just want to make sure x is going to a positive infinity. So if you plug in an infinity here, that's going to stay positive in the bottom. And if we plug infinity up here, 3 times infinity, that's also going to be positive. So we know our final answer here will be positive. So let's do the same thing now going to negative infinity. Okay, so just check exponents are the same because the 1 and the square root of x squared gives you a 1 also. So we're going to divide these coefficients. So again, it's going to be 3 over the square root of 2. But now you have to check. We're going to negative infinity. So if I plug a negative number into the denominator, that negative will get squared and we're going to get positive. So we will be left with a positive value in the denominator. And in the numerator, if I plug a negative value in for x, it's going to make the numerator negative. And so all in all here, we're going to get negative 3 over the square root of 2. So just be careful with those negatives. And if you check our graph, you can see here going to negative infinity does give us a negative value, and going to positive infinity is going to give us the positive value. Go ahead and try C and D on your own. See if you can come up with the two different horizontal asymptotes by finding the limit as x approaches infinity and negative infinity. Alright, welcome back. So you should have found this as an eats DC. Exponents are the same. So it's 1 over the square root of x squared, so 1 and 1. And so when we divide our coefficients, we get 1 over the square root of 9. And when we substitute a positive value in for x, we do get positive 1/3. Now over here, if we substitute a negative value in for x, we get a negative divided by a positive, so we get negative 1/3. Next we want to talk about infinite limits at infinity. And it says no polynomial function has a finite limit at infinity. Rational functions whose numerator has a higher leading coefficient than the denominator don't have a finite limit at infinity either. That's the big on top. So the end behavior of these functions can be made with this notation. We can either say that it approaches infinity or negative infinity. So if we look at letter A here, it says find the limit of x cubed as x approaches infinity. So we just think as x increases without bound, what happens to our function? Well, x cubed also increases without bound. And so when this is the case, we know that this limit we can write with the notation equals infinity. For letter B, here, as x decreases without bound, okay, and it decreases because we're going to negative infinity, what happens to x cubed? Well, we know when we cube a negative number, it stays negative. And so x cubed also decreases without bound. And so this one we can say equals negative infinity. Now, this was a polynomial function, so we knew it either had to be infinity or negative infinity. And notice as we draw the graph here of x cubed that we can see visually this is the case. Now in our next example, here we have a rational function where the exponent is bigger on top. And so when it's big on top, the limit doesn't exist, but we can still use our notation of infinity or negative infinity. Now one way that you can solve this is by actually performing the long division here. So we're going to set up our long division, 2x squared minus 4x. We're going to divide it by x plus 1. And we just say x goes into 2x squared how many times? Well, 2x times. And then we multiply 2x by x plus 1. So it gives me 2x squared plus 2x. And then we have to subtract this. So I go ahead and change the signs of both of these. And I like to always circle when I change my signs. Now this drops down to 0, which is what we want. And negative 4x minus 2x is negative 6x. And now I say x goes into negative 6x how many times? Well, negative 6. And so now I multiply negative 6 times x plus 1. And so I get negative 6x minus 6. And then because I'm subtracting, I'm going to change both of these signs. And again, I circle those there. So we get 0 and then plus 6. Now x no longer goes into 6, so we just write this as a fraction plus 6 over x plus 1. Now, what we did here is we know that this function and this function are the same thing. And so we're going to rewrite our limit now using our new function, the limit as x approaches infinity of 2x minus 6 plus 6 over x plus 1. Okay, so as we look at this, this is going to be 0 here. This would be negative 6. And this part right here, well, it's just our polynomial function, 2x. And if x keeps increasing, this function 2x is also going to keep increasing, so we get infinity. And so we do write infinity for this one right here. So we can write equals infinity. Now for example 2, we've already done the long division, so we're just really going to write our limit with our new function. So x is approaching negative infinity of 2x minus 6 plus 6 over x plus 1. And again, here this is going to give us 0. This is going to give us negative 6. And this one, as x decreases without bound, 2x will also decrease without bound. So here we get negative infinity. So all in all, we get our limit is negative infinity. So what this statement is saying, and by doing the long division, as x approaches plus or minus infinity, the function 2x squared minus 4x over x plus 1 behaves like the function 2x minus 6. So notice this part really didn't matter. So this function is now behaving like this function, and this actually becomes our slant asymptote right here of y equals 2x minus 6. So if we were going to draw a graph, we could draw the line 2x minus 6. So let's have this here at negative 6. This will be at 3, 0. And this would actually become an asymptote. And this function, if we were to graph it, actually looks like this. Not very exact with our max and mins, but the end behavior, this would start following this line right here and right here. So that's how you deal with infinite limits at infinity and finding slant asymptotes.